Okay, it looks like everyone has gotten settled. So welcome everyone. I'm Tony Ramajan. I'm the interim director here at the Green Bank Observatory. And as you can see, we're getting a little bit of weather outside today. But just a couple of updates of what's going on around the site. If this is your first webinar, you will we are updating the infrastructure on the Green Bank telescope. And one of the things we're doing that's taking a lot of time this summer is painting. And the status of that is we're basically almost done with our sandblasting of the upper feed arm, and we're going to start painting here in the next week or two. So that's good. We've also been very active in our foundation repairs and looking at and leveling the track over the course of the last several weeks as well. That's also been going very well. And next month, we're going to be working on wheel replacements. As you know, a couple of years ago, we had one of the wheels that failed, and we have all brand new wheels, changing the tires and everything on the GBT, make sure it's going to be good for us for the next several decades. Science side, prep continues for the 26A proposal call. Remember that call closes on Wednesday, July 30th at 5 p.m. Eastern time. So if you have any questions or if you have any problems with submission or just need plain help on submitting a proposal to the GBT, reach out and let us know. We're here to help you. In support of our upcoming 26B start of observing, we're going to hopefully start up observing last week in September, early October. We are going to have a remote observers training workshop. Now, we haven't set the dates on that yet, but keep an eye out for that because that'll be coming up here this fall. And we're here to help. So whether it's data processing, visiting the site, we'd love to have you come out and visit and work on papers, collaborate with the scientific staff here, submit a help desk ticket, and one of our support staff here at the Green Bank will follow up with you as soon as possible. So just consider that, and especially now that we're going into the proposal call, we're here to help you prepare proposals, set up your observing for observation on the Green Bank telescope. So with that, I'm going to hand over to Jay, who will introduce our speaker today.
Thanks very much. Our speaker today is Erica Behrens from the University of Virginia, and she'll be speaking about probing the kinematics of multiple and single protostar systems in Perseus with N2H+. Let me remind everyone to submit your questions through the Q&A button at the bottom of the screen, and we'll get to those at the end of the presentation. And also, this presentation is being recorded, so you and your students will be able to see it online in a few days. Take it away, Erica.
Great, thank you. All right. So thank you again for inviting me to speak today. Again, I'm Erica Behrens. I'm a final year PhD student at the University of Virginia. And I actually normally work with Jeff Mangum at NRAO, and I do extragalactic astronomy in nearby galaxies, mostly molecules. But I had the opportunity to work on this side project a few years ago in my PhD, and I worked with Adele Plunkett at NRAO as well as Zian Li and Che-Yu Chen at University of Virginia. So today I'm going to talk a little bit about the kinematics in these protostar systems and how we looked at them with N2H+. So from a very high level, we understand the process of star formation. We know that gas and dust molecules will collide and come in close proximity and stick together, forming clumps and then clouds. These clouds have to collapse in order for them to form stars, but there's this fight between gravity and pressure or turbulence. But eventually, if gravity wins out, then we do in fact form stars. But we know from high resolution observations that this picture is actually a lot more complicated. Within clouds, we see these, complex filamentary structures. We see lots of different protostellar systems, some in close proximity, some not. And within those protostellar systems, we see that sometimes we have multiple stars forming in one system. So there's a lot more factors to consider than just the gravity versus pressure debate. So some other factors that influence star formation. One factor, which is really many factors that I actually work on in my extragalactic work, is feedback from nearby star formation. So turbulence injected from supernovae or outflows, ionization from UV rays, cosmic rays, etc. The thing that no one likes to talk about, magnetic fields, but which we know are a very important part of star formation. And then what I'm going to talk about today is core rotation and how that influences the kinematics and the formation of stars. So some previous work by Che-Yu Chen, who was previously at the University of Virginia, used some GBT data from Argus to look at several protostars in the nearby molecular cloud Perseus. She used N2H plus. So you can see on the left, this is the integrated intensity map of the N2H plus 1 to 0. And on the right, we have the velocity information that we can glean from that spectra, so the centroid velocity. Shown here with the red and blue, and you can see the black lines show the direction of the velocity gradient, whereas the red and blue arrows indicate the direction of known outflows. So basically, we're seeing that the outflows are perpendicular to what we can assume is the disk, and this follows what we understand about solid body rotation. However, other sources within these data showed a very different picture. So this is NGC 1333 IRAS 7, which is also in the Perseus molecular cloud. So this is a multiple protostellar system. There's nominally 3 main protostars, per 49, per 18, and per 21. So these two, per 18 and per 21, are class 0 sources, just like per 30 and per 49 is a class 0 or 1 source. But we know that 2 of these sources actually have companions. So there's potentially up to 5 stars being made in this system. And the velocity information that we got from these original GBT observations was very complex and very confusing. You can see that it's not a clear, red shifted to blue shifted gradient. It's much more complex. And in fact, you can see from the outflows with per 21 that they're actually oriented in the same direction as the velocity gradient, which does not make sense. It would seem like the outflows are coming out in the same direction as the disk. So naturally, we were confused. Che-Yu Chen was very interested in following up on this. So she submitted an ALMA proposal in 2019 to get higher resolution N2H plus data of both per 30 and IRAS 7. All right. So this increased our spatial resolution by a factor of 3. So going from something like 2700 AU to 900 AU. Again, the same cores I mentioned as before. And again, targeting that N2H plus 1 to 0 line. And if you're not super familiar with N2H plus, it's very useful because of its hyperfine structure. So within the galaxy, we see that it has these hyperfine lines. N2H plus is being emitted from the very cold, dense gas that we see around usually class 0 protostars. But if you fit these spectra, then you can get the centroid velocity. And so that gives you a very precise measurement of the velocity structure and the kinematics. Oops. So we start with this GBT data. This is essentially the same as what I showed before, just my own plot. And once we get this higher resolution data, we see a lot more structure in these protostars than we saw before. So for instance, with per 30, you can really see the crescent shape of this protostellar core. With per 18 and 21, before we weren't actually able to resolve the separation between them, but we can now, which is pretty exciting. And we see that it has this even like complex morphology structure to just the gas itself. So showing that in a little more zoomed in. But something that you might notice is that even though we have better resolution here, we're missing a lot of flux from the outsides and the edges of these cores. So, the GBT being a single dish can theoretically capture all of the flux we're seeing, but since ALMA is an interferometer, we're not sensitive to every single spatial scale. So we're missing some of those larger scale structures. So ideally, what we'd like to do is combine these data so that we can be sensitive to all spatial scales and understand the kinematics across spatial scales. So from the envelope down to the core and maybe even the disk. And I did this using the feather method in CASA. So I actually combined the baselines in Fourier space using the GBT and ALMA data so that we can probe these kinematic structures across all scales. So I have ALMA in the top row, GBT in the middle, and then feather at the bottom. And so you can see that we still retain that high spatial resolution from ALMA while still being sensitive to the larger scale gas structure. Again, probing the kinematics across all scales. So what we did after combining the data was fitting the spectra. So this is towards per 18. And we fit the spectra and the ALMA, GBT, and feather data using PySpec kit from Adam Ginsberg. So you can see the parameters that it gives us back here. We're most interested in the velocity, which you can see it seems like we're constraining to very high precision. So yeah, we get a centroid velocity at every single pixel in this map. I'm just here showing the results towards a single pixel. But ultimately, if we fit the spectra at every single pixel in these maps, we can get these really cool centroid velocity maps. So you might notice from before that it's a similar structure as what we saw with just the GBT data, but obviously at that higher resolution. And so before, whereas we just saw like a solid red shifted component, a solid blue shifted component, we can see that even within those components, the gas is moving at slightly different velocities in our isolated protostar. And we see that the kinematics in this triple system remain extremely complex. So we're not seeing something that looks clearly like rotation. We're not seeing that the kinematics are completely linked to the core rotation, like we might have initially thought with just the GBT data. Instead, the kinematics are very complex, very chaotic. We can look at this in a little more detail by looking at linear velocity gradients. So to do this, we take the centroid velocity at every pixel and we calculate velocity gradients. And then to get a linear velocity gradient, we average those velocity gradients within a given area. So in this case, this is a 10 arcsecond radius circle centered on per 21 in this case, but we looked at all the protostars. And it not only gives us the magnitude of the linear velocity gradient, but it also tells us the direction. So here I'm showing the direction of the velocity gradients for ALMA, GBT, and then this fatter arrow is for the feather data. So something to notice is that between the small scale structure that's probed with ALMA and the larger scale structure probed with the GBT, we're seeing very different directions in the linear velocity gradient, which would suggest that the gas on small scales and large scales do not follow the exact same kinematics. But regardless, if we look at position velocity diagrams along that axis of the linear velocity gradient, we can also see that the velocity structure that we're probing does not appear to be a result of rotation. PV diagrams have a very predictable pattern when we see rotation, and that's not what we're seeing in these maps. So ultimately, it's looking like the velocity structure that we're probing, both on the small scales, large scales, and in our combined data, do not show any kind of coherent rotation. So what is this actually telling us, and like what are we actually seeing with our velocity structure? We should note that other studies have also shown that on scales of about 1,000 AU or greater, you can't really see core rotation. The velocity structure is not probing core rotation, it's probing other processes. So those can include turbulence, especially in multiple protostellar systems like IRAS 7. Several of these have outflows. Again, they have companions, so it's a very complex system. Torques, again, from nearby protostars or other overdensities in the gas, and potentially also non-axis symmetric collapse. So this is one suggestion for how disks can get their rotation if it's not inherited from a larger scale cloud or filament. If there are, again, certain like overdensities in the gas or a non-homogeneous density distribution, it can cause these cores to collapse, and that can actually lead to the rotation, indicating that likely the rotation that we see in disk scales or core scales is not inherited from larger scale structures like clouds or filaments, that they're actually totally separate and they don't have any impact on one another. So I will leave my takeaways up. Ultimately, N2H Plus is a pretty powerful tool for probing the velocity structure in galactic protostars. This is not, unfortunately, so helpful in extragalactic. I mentioned that extragalactic is actually my main thesis work, and we don't really get the hyperfine structure in extragalactic protostars, excuse me, extragalactic star-forming regions, but it's a really powerful tool within the galaxy. So our GBT and ALMA combined data do not show any signs of rotation on scales of 900 to 2700 AU, but it's likely that if we were going to see core rotation, we would have to go to even smaller spatial scales. And probably the disk and core rotation is not going to be inherited from larger scale structures, and that they're relatively independent from one another. So yeah, now I will take any questions.
Thanks. Thanks very much for a most interesting presentation. Please submit questions through the Q&A box at the bottom of the screen. And we have one here already. Are the disk inclinations known for these objects?
Yes, I believe they are. So I don't have the numbers off the top of my head, but I know John Tobin has a pretty extensive paper, I think using from the Van Dam survey, maybe using VLA data. And so I think for most of these, the disks have been resolved and their orientations are known.
I know that it's been suggested in the past that molecular clouds have an overall, on the largest scale, net rotation just because of galactic shear. Do you have enough data on the smallest scales? What you're suggesting is that the orientations of the disks on the smallest scales would be completely random with respect to this.
Yes, that is what I'm suggesting. So I mean, we're not potentially seeing down to the level of the core or the disk, but we are seeing across these spatial scales that the velocity structures are not necessarily related from the cloud scales to the core scales. So showing, for instance, this plot, you can see that the velocity structure from between ALMA and the GBT do not seem to be aligned at all. So at least from those scales, it doesn't seem like rotation is transferred down to, smaller disk scales.
Yeah, here's another question. In all three protostar cases, their positions are offset from the peak of the integrated intensity of N2H plus.
Yes.
Are the protostars more coincident with the local peak of N2H plus column density?
So what we've determined from this is that likely there's a couple suggestions here. One is that around the protostar itself, it's too hot for the N2H plus to survive. So N2H plus is largely destroyed, which is why we see it offset from that peak and why, in particular, we don't see a lot of N2H plus around per 49, which is a class 0 or 1 protostar. But it also could just be confusion of line of sight. We're not totally sure, but we did also notice that as well and thought it was an interesting feature.
Okay, and we have another question. When you average the gradient in centroid velocity over a solid angle, what was the typical standard deviation of the gradient directions?
So this depended drastically based on the size of the circle. So I showed here only the 10 arc second circle, but we actually probed this from 5 arc seconds to 30 arc seconds. And if you're interested in the exact values, you can check out a table in my paper. But basically, we found that on smaller scales, or excuse me, on larger scales, the velocity information seemed to be more coherent and the standard deviations were smaller. So say if the linear velocity gradient had a value of 9 or 10, the standard deviation might be something like 4 or 5. But on the smaller scales, the gas seems to be far less coherent to the point where the standard deviation would be like 10 or 100 times the calculated value. So really, really large on the small scales, indicating that we're seeing a lot more incoherent, complex kinematics on the small scales compared to the large scales.
And another question, is the velocity field consistent with that of cone-shaped outflow lobes?
That's a good question. So I know that let's see if I can go back here. I know that per 18 is thought to have a north-south outflow. So you see this V-shaped structure here. So that could be consistent with a cone-shaped outflow lobe. I think per 21 might have a structure, or excuse me, an outflow more along this angle. So it's somewhat consistent with our velocity field, but not fully. It could also be that what we're seeing is a combination of the outflows from several of the protostars.
Okay, well, that appears to answer all our open questions. Let me wait just a minute or two to see if any come in at the last minute. And while waiting, just to remind you that 2 weeks from now, we will have the next of our talks in this series by yours truly. And I'm looking for the title. So you should take a break. It's proposal deadline date for all of the NRAO telescopes. But you can take a break and listen to me talking about observations of neutral hydrogen outflow in the Milky Way's Fermi bubbles. Well, as there are no other open questions, let me thank everyone for attending and thank again you for a wonderful presentation. Just to remind everyone that this presentation will be visible on our website within a day or two. So we look forward to seeing you again in 2 weeks. Thank you and goodbye.